So when I was going through our lectures, I realized that we had done an example problem for a closed system where we had water inside our system, but not one where we had an ideal gas inside our system. So I wanted to give you one more example here of a first law problem where we have gas inside of a piston and cylinder. So we start at state 1 with a pressure of 80 psi. So that means this is in imperial units. We have a volume initially of 0.1 cubic feet, and our mass is 0.01 pounds. At state 2, we have a pressure of 14.7 psi. That's atmospheric pressure. And we're told for this process, as we move from state 1 to state 2, that P times V to the power of 1.5 is constant. So we do have a relationship between pressure and volume. We're also told that for air, which is what's in our cylinder, the specific gas constant, R, is 53.35 foot-pounds per pound mass Rankine. I'm asked to find, with constant and variable specific heats, the work performed in the system and the heat transferred to the system. So I know that the change in energy in my system is a result of heat coming in or work going out. I'm going to assume that kinetic, potential, and spring energies are all very small compared to the change in internal energy in my system. So I get that delta U is equal to Q minus W. Unfortunately, at this point, I don't know U2, I don't know U1, I don't know Q, and I don't know W. So the good news is that I have an equation. The bad news is I don't know any of the terms inside that equation. So I'm going to start off by trying to find the work. I started with work because I know the integral, or I know the equation here is the integral of P dV, and I also know that for my process, I have a relationship between P and V. So P as a function of V is equal to C divided by V to the power of 1.5, or that C times V to the power of negative 1.5 is equal to PV. So now I can put that relationship into my integral. I know that C is constant, so I pull it out of my integral, and I see that C is equal to the integral from V1 to V2 of V to the negative 1.5 dV. I can integrate here, and after I do that, I see that C times V2 to the power of negative 0.5 minus C times V1 to the power of negative 0.5 divided by negative 0.5 is equal to work. Now, I remember here, I've left this C just as a constant, but I remember that this constant is equal to P1 V1 to the power of 1.5, but it's also equal to P2 V2 to the power of 1.5. So I'm going to match up the subscripts here so that I use, in the first time that I use this constant C, I use P2 V2 to the 1.5. And the second time I use the constant C, I'm going to use P1 V1 1.5. So when I do that, I get P2 V2 minus P1 V1 divided by negative 0.5 is equal to work. So this is good because now I have an equation for the work. I know P2, I don't know V2, I do know P1, and I know V1. So I need to be able to find V2. Now again, I'm going to use the relationship that P1 or that PV to the power of 1.5 is constant. I don't care what the constant is here, although I could figure it out if I wanted to. I'm going to get a symbolic solution for V2. So here I isolate for V2, and I see that V2 is equal to P1 over P2 multiplied by V1 to the 1.5, all to the power of 1 divided by 1.5. I can work this out on my calculator, and I see that V2 is 0.3 cubic feet. So now I can go back to my work equation. I know all of the information here. The one thing I do have to do, so it's always important to carry units in my calculations. If I just wrote the P times V, my pressures are in pounds per square inch, and my volume is in cubic feet. So I'd get this pounds cubic feet per inches squared, which is not a real unit. So now I know that there are 12 inches in a foot, but I want to get rid of inches squared. So my 12 squared times inches squared is up on the top, and I divide by feet squared. I do this for both of my terms, and then I get this number here, that the work is equal to 1,034 foot-pounds. So that's good. I've got my work, and this work is positive. So I know that work in is negative, so this must be work out. So my system must be doing work on the surroundings. Next, we want to apply our first law. So I know that U2 minus U1 is equal to Q minus W. I still don't know U2 or U1. I still don't know Q, but I do know W, so I'm making progress. Now, I want to be able to find delta U. The problem asked me to do this in two different ways. So first, it's going to ask me to assume constant specific heats. Now, whenever a problem says use constant specific heats, it means use CV times delta T is equal to delta U. So we'll do that here. So now my delta big U becomes mass times CV times delta T. I do know the mass. I know T2, or I don't know T2. I don't know T1. I do know CV. So now I got to use the ideal gas law. Now there's a couple different ways we can use the ideal gas law, but in this case, I'm going to look just at state 1, and I'm going to see that P1 times V1 is equal to mass times the specific gas constant times T1. The only thing I don't know in this equation is T1. So I'm going to put all of the information that I know into this equation. Again, I got to recognize that my units here are a little bit weird because I have pressure in PSI and volume in cubic feet. So I got to, again, play around with the unit conversions until things look nice. And now I can put this information in my calculator, and I get the T1 is 800. And I get the T1 is 866 degrees Rankine. Now it's important to realize that this equation, because there's no delta T in this equation, so this equation will always, every time, give me a temperature in degrees Rankine. Or if I'm using it in metric units, it will give me an answer in degrees Kelvin. So whenever I have an equation where the temperature stands alone and it's not a change in temperature, I either want to put in an absolute temperature or I'll get out an absolute temperature. And absolute temperature scales have absolute zero as 0. So now I know everything in my equation that I need to know except T2. So here we'll use the ideal gas law again, but we'll kind of manipulate it a little bit. So if P1V1 is equal to MRT1, but M and R don't change, so M and R are constant. So that means that P1V1 over T1 is equal to MR, but MR is also equal to P2V2 over T2. And here, I don't actually care about the MR in the middle, but I see that P1V1 over T1 is equal to P2V2 over T2. So here, the only thing that I don't know is T2, so I set this equation up as T2 is equal to T1 multiplied by P2 over P1 multiplied by V2 over V1. I know all of this, so I can put it into my calculator. I like to do it this way because here, now, as long as my pressures are in the same unit, so I'm still using PSI here, but because both my pressures are in PSI, the units just cancel out. So this P2 over P1 is actually a dimensionless number. So as long as my pressures are in the same unit, then I'm okay. Same with my volumes. And here I see that the temperature, T2, goes down a little bit to 477 degrees Rankine. So now I know everything that I need to know to calculate delta U. So delta U is equal to M CV times delta T. I know all of this information, and I see that delta U is minus 517 foot-pounds. So this tells me that the energy is decreasing in my system. And I could see that because T1 was bigger than T2, so my temperature is dropping. So now I know delta U, I know W, but I don't know Q. But that's okay, because now I have one equation and one unknown. So I'll isolate for the heat transfer from state 1 to state 2, and I get that this is U2 minus U1 plus W from 1 to 2. I know that delta U is minus 517 foot-pounds, and I know that the work is 1,034 foot-pounds. So in total, I see that the heat, as I go from 1 to 2, is 517 foot-pounds. So heat in is positive, so this must mean that heat is entering into my system. So 517 foot-pounds of heat are entered into my system. So now, how would I do this problem if I was using variable specific heat? So basically the problem would be exactly the same up until the point where I've calculated work. I would come to this point where I say, oh, I would like to find delta U. But now instead of finding delta U as CV times delta T, I'm going to say that there are variable specific heats, so that the specific heat is a function of temperature. And if specific heat is changing with temperature, I can't use CV times delta T without doing some calculus. So instead, I'm going to look up specific internal energies on table A22. Now in this case, because we're using imperial units, we're going to use table A22E. E is for English units. So here's my state table. I still have, so I used the ideal gas law to find these temperatures and this volume, and none of that is going to change because I didn't have to use CV to get any of that information. So all of that stays the same, and I just have to find U. So this is table A22E. I just took a snip of this. I see I'm going to find the specific internal energy at state 1 where the temperature is 866 degrees Rankine. So here it's important to see that we have temperature in Rankine. So that's in the header for this table. It tells us the temperature is in Rankine. So if you're looking in Fahrenheit, you'll have to convert that using the conversion that's on your exam review sheet. So now I have 866. So that's between 860 and 880. The nice thing about using ideal gases is that the only thing that I need is the temperature. So once I know the temperature, I can fix the state on table A22, or I can use CV times delta T. But in this case, we're using variable specific heats. So now I know, because my temperature is between 860 and 880, that my specific internal energy is going to be between 147.5 and 151. So I need to interpolate. So I get my interpolation factor A. So this is 866. That's the temperature I know, minus the temperature bounds that I have. And this is going to be 6 over 20, or 0.3. And then I use that interpolation factor in this equation. So this is now going to be my minimum value of U plus A times delta U on my table. I work this out and I get that U1 is equal to 148.6 BTU per pound mass. So I put that up on my state table. Now I want to find specific internal energy of state 2. So I'm going to do the same process, but now my temperature is 477 degrees. So I look here, 477 is between 460 and 480. I'm going to use a different interpolation factor, B, and that interpolation factor is 17 over 20, or 0.85. I put that into my expression for the specific internal energy as I'm interpolating with this factor B, and I find that U2 at 477 degrees is 82.37. So I do notice here that U2 is less than U1, and that's encouraging because when I did the problem with constant specific heats, I found that delta U was negative. Now the magnitude's different here. So here I can see that my delta U is equal to mass times the change in specific internal energy. I can rearrange for Q because Q is the thing that I don't know here. So Q is equal to M times the change in specific internal energy plus the work from 1 to 2. That equation now came up here to the top. And now hopefully I have all the information that I need. So I know the mass, I know the change in specific internal energy, and I know the work. So when I work this out, I get to this problem. So before, I saw that my delta U was something like minus 500 and something when I was using constant specific heats. And here it says it's minus 0.66. My work is still 1,034. And if I wasn't tracking the units in my calculation, I would probably, or at least potentially, make a really big mistake here. But here I see that it makes no sense to add British thermal units, or BTU, to foot-pounds. So I have to convert BTUs to foot-pounds. And this is really weird. Like, this is another thing that, if you don't love the metric system yet, you certainly will after you do some more imperial problems in this class, because these conversions make no sense. There's 778 foot-pounds in a British thermal unit. So that's what we have to do. We're trying to get rid of these British thermal units. So we put British thermal units here on the bottom, and there's 778 foot-pounds in a BTU. So now my BTUs will cancel. Here again, I can do some math so that I can be adding apples to apples here. And I get that negative 515.3 foot-pounds plus 1,034 foot-pounds is equal to Q. So here now I'm starting to feel better about this answer because once I've converted the units, my numbers are starting to look the same. I find when I'm using variable specific heats that Q from 1 to 2 is 518.7 foot-pounds. I think we had something like 517 foot-pounds for constant specific heat. So this makes me feel really good because I got basically the same answer when I did the problem in two different ways. Again, I see that heat in is positive, so heat must be added into my system in this process. So hopefully, after you see this review and a problem like this, where we did an imperial problem, where we had to play around with units, and we used an ideal gas, so hopefully after doing this, you feel pretty confident headed into the first exam. Good luck, and I'll see you next time on Thermodynamics.